Hello folks, this is 2020 October November paper 42 and the question number is 9. It is concerned with the chapter magnetic field. So it says that a small coil, this one, is placed close to one end of a solenoid. So this is the solenoid connected to a power supply. This is the power supply. The plane of the small coil is normal to the axis of the solenoid. So this is the axis of the solenoid. So the plane of this coil, is somewhat like this. So this is the plane of the coil. So it is normal to the axis of the first coil, as illustrated in figure 9.21. So then, then the power supply causes the current I in the solenoid to vary with time t as shown. So we have the power supply here, it supplies current here, and the current varies as such. So this is the type of variation of current. So till a certain time here, 1 square left of t1, the current is 0. Then after 1 square right of t1, current rises uniformly to a maximum value. Then it remains constant at maximum value. Then from this half square here, it decreases to again 0 and it remains constant. So this is how the current varies. So initially constant at 0, rises up to a certain value uniformly, then again constant here, and then falls uniformly to 0 and then again remains at 0. Then state Faraday's law of electromagnetic induction. So it is about EMF. So we have to mention the EMF, and this EMF is equal to the rate of change of magnetic flux linked to the coil and so on. So I won't go through this in detail. So what I should do is, the main stuff is this. So it says on the axis of 9.3, sketch a graph to show the variation with time t of the electromotive force EMF induced in the small coil. So we have to go for the graph of EMF. Now we have to remember that this EMF is equal to minus d phi by dt. It is equal to the negative rate of change of magnetic flux lines linked to the coil or incident on the coil. And this phi is equal to B into A. And since it is perpendicular, I can just avoid the factor cos something. So it's just B into A. And this B again depends on the current. This magnetic field again depends on the current. So current flowing in the first coil. So that's why overall they should be equal to some constant KIA. So that means phi is proportional to this I. Now our E should be proportional to minus di by dt. It should be equal to the negative rate of change of current. So now till 1 square left of this t1. So till 1 square left of this t1. So this thing here. And in this graph, I have to pinpoint this point here. This point. So till this graph, we have a constant value of I at 0. So it should be our this thing should be equal to 0, 0, 0. So the value of EMF should be equal to 0, 0, 0, 0, 0, 0, 0 like this. So during exams, you use a straight ruler or scale like this. Now again here. From here to here, we have again constant value of I. So if I is constant, the value of E should be 0. So if I is constant, the value of this E should be 0. So again here also it should be 0. So from here, so I can use 0. So 1 square right of this T1, 1 square right of this T1. So from here till this half square, again it is 0, 0, 0, 0 like this. So it is 0 0 0 0 0 0 0 0 0 0 0 like this. And again from this half to half here, it should be 0. Again it should be 0 0 0 0 0 0 like this. It's all 0. Now near about this time t1, one square left and one square right, there is a positive slope here, positive slope. So what I must have is here, here, di by dt is equal to positive. Di by dt is equal to positive. So this should be positive. So I must have e equal to some negative value. So this slope is constant at that moment, straight line, slope is constant. So that's why e should be negative of constant. E should have some negative value constant. So let me say, let me give it a value like this. Haphazardly, I give it like this. So from here to here, it goes to negative value suddenly, and here again it goes to 0 suddenly like this. Now, on the other hand, so around the vicinity of this t2, what we must have is, so if I calculate the slope here, here for the same vertical change, it goes through two squares. But here, for the same vertical change, it goes through only one square, half of this to half of this. So that means this slope is double. The magnitude of this slope is double. So the value of EMF also should be double. EMF should be double, and it should be positive this time because it is negative of negative slope. So it will be positive. So that means, so here I have this value here. The value should be this much. So it rises like this here and then here. So it will be, so from down it will rise like this. So I feel comfortable drawing from above, so like this, and then it will be like this, and then it is like this. So this is the graph for the EMF. So it is constant at 0, then constant at a certain negative value, then again constant at 0, then constant at some positive value but double of that negative, and then again constant at 0. Then the small coil in A is now replaced by a Hall probe, a different thing. The Hall probe is positioned so that the reading for the probe is maximum. It's a hit and trial method. The current I in the solenoid varies again as shown in figure 9.2. So the variation of current is same. So here again I have to draw the graph. So what we have is VH is equal to, this VH is equal to, BI by NQT. Everything is constant, so I just have to go through this I. So it has to follow, so this VH is proportional to this I. It will follow the variation of this I. So it's the same pattern here. So from here to here it will be, so from here to here it will be 0 0 0 0 0 till here, and here it will be maximum here, maximum from there to there, max value like this, again 0 value like this, and from here it goes rises straight like this, and then it falls straight like this. So it has to follow the same pattern as the pattern of current. So this is the answer to this question.